Good morning, or good afternoon, or I guess whatever's appropriate for the time zone you're listening to this in. My name is Aaron Glanville. I'm a PhD student at the University of Queensland, and today I'll be sharing a bit of the work that we've done looking at the potential impact of systematic redshift offsets in our measurements of the baryon acoustic oscillation future, and the potential impact this could have on our cosmological constraints. Now, before I start, I'd just like to thank the organizers for hosting this event. I'm really looking forward to trying out the interesting format of this conference, and who knows, maybe we'll find some nice upsides to online conferences that we can hold on to once this is all over. So let's jump straight into the physics. As I'm sure you're all very familiar with, cosmology at the moment has a bit of a tension on its hands. See, our measurements of the present-day expansion rate of the universe seem to be in disagreement, and this is obviously not something that we would have expected or anticipated. Now, part of what makes this problem so difficult is that you can slice this discrepancy in a number of different ways. You could look at it as a disagreement between standard candles versus standard rulers, and spoiler alert, I'll be focusing on this a lot in my talk. But you could also see it as a disagreement between early universe versus late universe physics, or as a disagreement between global versus local constraints. Whatever it is, we know that our measurements of this present-day expansion rate are in disagreement, and as the measurement precision and accuracy on our constraints have improved, the statistical significance of this discrepancy has now kind of reached the point where we're pretty confident that there's something going on here. So it's been said that if you ask 5 people the same question, you'll frequently get 10 different answers. And this also seems to hold true for our treatment of this Hubble tension. An absolute mountain of different proposals and ideas have been put forward in the literature to either explain why this tension exists or to try and ameliorate it. But I think you can broadly categorize these into 2 different streams of work. You've got a strong effort on the theoretical side to fill out what could be an incomplete theoretical picture. And you've also got a strong effort from the observational and analysis side, trying to find the smoking gun that once accounted for will bring our measurements back into alignment. And second spoiler alert, this observational and analysis side is mostly what I'll be focusing on in my talk. So we generally think that our measurements of the BAO feature are quite robust to a wide array of known observational effects. So when we discuss efforts to try and improve our observations, usually we'll do something like bring out our Hubble diagram. We might bring out our Hubble diagram and we might talk about some new distance calibration that improves our y-axis, trying to reduce the error bars along our y-axis here. But I think that there's another side to this equation that we really should be considering, and that's our measurements of redshift. Redshifts can contain biases and potential sources of error, and I think that they might be worth considering. So by the end of this talk, I hope I can convince you that not only can probing a little deeper into our redshift measurements be worthwhile for these kind of standard candle constraints, this kind of Hubble diagram picture here, but I think they can also go a long way towards improving our confidence in our standard ruler measurements, making us feel a bit more confident in the robustness of our BAO constraints. So there's already been quite a bit of effort to look at the potential impact of a systematic redshift offset on the constraints recovered through supernova cosmology. So, looking at what would happen if there was some phenomenon that was offsetting our redshifts, uniformly pushing them or reducing them in magnitude. So this is something that's already been studied in the context of supernova H0 constraints, and these have found that surprisingly small systematic offsets, of an order of 10 to the negative 3 to 10 to the negative 4, these kind of small but systematic offsets have an amplified impact on the final cosmology that you recover, biasing constraints on H0 by up to 1%. Now, what's interesting is that this sensitivity to, observational level redshift offsets extends beyond just H0. And these kind of studies have found that these kind of observational redshift systematics or potential redshift biases, these could offset constraints on omega M and W as well. So this is a pretty broad effect that they're discussing here. So we know from the literature that small but systematic redshift offsets could significantly impact the constraints recovered through supernova cosmology and could bias our value of H0. But what about the other side of this tension? Could standard rulers, like measurements of the BAO feature, could they also be sensitive to the kind of redshift errors that we're talking about here? Now, this idea of some undetected redshift offset, which is affecting both our standard candle and our standard ruler measurements, This becomes really interesting when you break down the kind of distances which are probed by standard candles and rulers. So standard candles, they probe luminosity distances, the distances associated with our distance, luminosity or flux relationships. Whereas our standard rulers, they probe angular diameter distances with a geometric origin. Now we know that at small scales, these give exactly the same results, and they're both perfectly valid ways of defining distance. But in any metric theory of gravity, so in our universe, the distances that are probed are redshift dependent, and they're dependent in different ways. So this means that if there was some observational level effect that was offsetting our redshifts, if they were offsetting our redshifts uniformly, then the distances that are probed by standard candles and rulers could, in theory, be offset in different ways. So this kind of mechanism really led us to the key question that we wanted to explore in this research. Could some undiagnosed or low-level effect be biasing both our standard candles and our standard rulers in such a way that it could contribute to this observed tension in H naught? So what kind of effects are we talking about here? What could be causing these kind of biases, and what kind of order of magnitude could they be? Well, we're mainly interested in observational level effects that could be uniformly or systematically pushing our redshifts to higher or lower values. So an example of something that might be on the larger end of what we're considering includes things like the low redshift approximation for velocity corrections in place of the full correction. So using this full equation when combining redshifts is important for a number of corrections. For example, when correcting our local bulk flow, or when quoting redshifts against the CMB reference frame. So when converting from a heliocentric frame to a CMB rest frame redshift. So as an example, if we use the low redshift correction for our CMB frame correction rather than the full equation, we'd get an error on the order of 10 to the negative 3 to 10 to the negative 4, depending on the kind of redshifts you're probing. And as we see on this plot here, this corresponds to an offset of several tenths of a percent at the kind of redshifts we're probing in CMB measurements. So this is the kind of effect we're interested in, very small but uniform systematic offsets on our observed redshift. Now, we might also expect some physical effects to introduce these kind of systematic observational offsets. If we lived in an over or under density, then there'd be an additional gravitational redshift that we would need to account for. But these kind of effects are probably an order of magnitude lower than the observational effects we're looking at. And so they're not really kind of representative of the major effects that we're looking at here. Now, a key caveat to this is that we're only focusing on systematic effects, effects that would uniformly offset our observed redshifts. So statistical errors, the kind of errors that result in symmetric biases or errors, these don't fall into the spotlight of our research. The kind of symmetric errors would average out and mainly serve to increase the uncertainty in our constraints. Whereas we're interested in systematics that could actually shift the position of the BAO peak and systematically offset the cosmology that we're looking at. So that's really the Gedanken experiment, I guess, in which we started this research. Could some low-level observational effect, which may have previously been negligible, could these be influencing our measurements of the BAO feature? Now, since we're interested in potential systematics which may have previously gone unnoticed, or been negligible, we start by limiting our study to simply determining how large an observational level systematic would actually have to be to significantly bias cosmology. Then once we have a better idea of the significance threshold, we want to take a step back and compare the magnitude of the offset that you would need to significantly bias your cosmology to the kind of physical effects that we talked about earlier. So our basic plan of attack is to take a mock survey and inject a bias of a known magnitude at the observational level. By propagating this sample with a known bias through a standard BAO fit and using these results to constrain cosmology, we can get a better idea of how sensitive the cosmology that we recover at the end of our pipeline is to the magnitude of offset that we inject at the start to try and better constrain this significance threshold we're looking for. So that's really where we started. Just like any other measurement of the BAO feature, our analysis began with the Galaxy Redshift survey. So as our baseline, we make use of the multi-dark patchy mock dataset constructed for the final BOSS data release, so SCSS DR12. Now these surveys were designed to replicate the redshift range from about 0.2 to 0.75, the survey geometry, the number density, and all of the physical effects associated with the true data that was used in their 2-point clustering statistics. Perhaps most importantly though, this survey was constructed using points, the points were populated using a fixed cosmology. And so this really made the patchy mock DR12 mock sample an optimal baseline sample to look at the impact of systematic observational level redshift offsets when all the relevant analytic and computational techniques that you need to analyze a true BAO survey are included. Now, from these mocks, we chose the Northern Galactic Cap, or NGC patch, with a survey footprint of about over 7,000 square degrees, given here. So this was the largest single patch available, containing nearly 1 million individual sources. Now, from this, we took 500 of these samples. So think 500 surveys of a boss level constraining power. And this formed our baseline sample. From this baseline, we then injected systematic biases in Redshift at the observational level to create a catalog of known biased surveys. So when I say that we injected at bias, what we did was we systematically offset our redshifts by some common factor at this kind of survey stage. So once we did this for a number of different injected bias magnitudes, so for different sized offsets, we had the catalog of known bias surveys that we could compare to the original unbiased patchy mock sample, which formed our baseline. So once we had our catalog of galaxy redshift surveys, the next thing we want to do is to measure the 1D matter power spectrum from these samples. And in particular, we want to compare the spectra that we recover from our baseline sample to those with an injected bias, I guess, as a bit of a sanity check. So we start by projecting our galaxy redshift surveys into a 3D box. And when we convert from distances to redshifts, we use the underlying survey cosmology, so the cosmology used to construct these mocks, as our fiducial. So we should have a pretty high quality sample here. And then we measured the 1D matter power spectrum from this projected sample. So for both of these steps, projecting our sample and measuring the 1D matter power spectrum, we made use of the publicly available N-body kit toolkit. And this is the kind of spectra that we recover. So the blue here, this corresponds to the matter power spectrum that we recover for our unbiased patchy mock sample. And this is the average of 500 power spectra. So we evaluated the power spectrum for each mock, then we averaged all 500 to create this, this blue line here. And this is flanked by our orange and our green samples. So these correspond to samples with an injected bias of 5%. Now, this is obviously much larger than the kind of offset that we're looking at, but it's just a really good illustration. Now, off the bat, there are two main things that we can see here. The first is that when we inject our bias, we see that we're uniformly affecting the amplitude of our power spectrum. So we're uniformly increasing or decreasing our clustering across all scales, and this makes sense. So that's really the first sanity check done. The other thing that you can kind of see here is that the positions of the peaks have shifted. Now, since most of the information that we're interested in is encoded in these peaks, is encoded in these BAO wiggles, we want to isolate them to get a better idea of what's actually going on. So after confirming that the systematic redshift biasing is affecting our 1D matter power spectrum and it's affecting it in a way that makes sense, let's now focus on extracting the cosmological information itself, extracting the BAO feature. To do this, we want to isolate the BAO wiggles by comparing them with the smooth linear template at the effective redshift of our sample. And in order to do this, in order to extract these features using a linear template, we make use of the publicly available modular BAO fitting code Barry. So once the BAO wiggles are isolated from the matter power spectrum, we see that our injected systematic bias results in a shift in the position of our peaks in K-space. So when we inject a plus 5% bias, when we increase our redshifts by a factor of 5%, we see that these peaks are being shifted to lower K modes or larger scales. And similarly, when we decrease our redshifts uniformly, we see that this clustering is being pushed to smaller scales. So this makes sense, and we're pretty happy with this data moving forward. So with the BAO features extracted, we want to use these to constrain our dilation parameter alpha, the main parameter which is actually fit by a BAO survey. And we once again fit for alpha using Barry. So we fit for alpha using our underlying sample cosmology as our fiducial, and we repeat this not only for our baseline sample, so our unbiased patchy mock sample, but for all of our samples with an injected bias. So here we plotted the size of the offset in alpha. So that's the alpha of our biased samples minus the alpha of our baseline samples as a function of our injected bias. And here we can see a nice linear trend between the two parameters. Now in this description, there is something I've glossed over, and that's the specific model that we actually use to extract these BAO features. So while similar, there's a number of accepted BAO models which all give slightly different values for alpha, and this is often quoted as a major source of theoretical systematics. Well, we find that these models do indeed give slightly different values of alpha. We find that the offset in alpha, this delta alpha parameter, is consistent between models. So to avoid over-reliance on any individual BAO model, we fit and use this delta alpha parameter moving forward in our analysis. So now we can move on to some of the interesting stuff, trying to fit cosmology from these results. So here we have the results from an MCMC fit of our BAO data with and without an ejected bias of plus or minus 2%. So the red contour is our baseline, and our blue and green are the fits that we get from an injected bias. Now, the most obvious effect that we can see is that our models with an injected bias are shifted along the omega m axis. But our BAO data itself isn't particularly constraining, particularly for our H0 parameter. So to get a better idea of how this would translate to realistically biased cosmological parameters, we need to fold in some information from other sources. And so we begin by folding in some of the CMB data from the Planck 2018 data release. So this is constraints from the BAO, from CMB, sorry, across high and low multipole number. So on the left, we have the overlapping constraints from BAO and CMB data. So just the plot from before with our BAO contours only overlapped with our CMB constraints. And on the right is the output from an important sampling of our Planck chains where we fit for the biased alpha parameters that we're looking for. Now, what we see here is that when combined with our CMB constraints, the injection of a systematic redshift bias in our BAO measurements offset both omega m and H0. And so this is the kind of effect that we're interested in, and we see that the shifts that we recover are pretty significant. For a plus minus 2% injected bias, we're seeing offsets on the order of 1 kilometer per second per megaparsec. Now, obviously, this plus minus 2% bias is far larger than anything that we thought might be plausible, maybe by an order of 10 times. And so we needed to repeat this for a variety of different injected offsets. And this is really the kind of final interesting plot that we got. So what we found is a consistent linear trend between the injected redshift offset and the recovered value in H0 and omega m. And we find that for offsets of the kind of magnitude that we think are plausible, on the order of 1 to 0.2%, the kind of injected offsets that we're seeing, that they're very negligible. And so this really seems to confirm that the BAO feature is very robust to not only a wide array of known systematics, but is robust to potentially unknown systematics that are affecting all of our redshifts uniformly. In order to get a 1 sigma offset in our value of H0, you'd need an injected bias at least an order of magnitude higher than what we think is plausible. So these really are pretty robust measurements when constrained using CMB data as well. With that said, however, BAO isn't just combined with measurements of the cosmic microwave background in a lambda CDM universe, and it can be used to provide insight into a variety of models. So I just quickly wanted to share one of the more interesting ones that we found. So when we fit WCDM models, measurements of the CMB alone only provide weak constraints on H0, and they're really a model where measurements of the BAO feature really help with our constraining power. So we wanted to know whether or not this dependence on the BAO feature made them more susceptible to potential redshift errors in our BAO analyses. And the short answer is yes and no. So the size of this offset's significantly larger. It's about double the size that we had before. But the constraints themselves are weaker. And so it's not statistically any more significant. And these measurements are still very robust. You need an order of magnitude offset to get cosmologically significant offsets in the constraints that you're recovering. So what's the key takeaway from this research? Well, we find that when systematic redshift biases are injected into galaxy redshift surveys, the cosmological constraints that we recover are uniformly offset. But we find that the injected systematics must be at least an order of magnitude higher than accepted systematic error budgets and plausible sources of these kind of systematic biases to significantly offset our cosmological parameter constraints. Now, this obviously doesn't mean that we don't have any observational level systematics, but it does suggest that their potential impact is limited on the BAO side. With all that said, however, as BAO surveys continue to reduce their statistical errors with improved precision and scale, unresolved systematics may play a proportionately greater part in characterizing our measurement uncertainties. And so there's something that we really should be keeping in mind as we look to the future. Thank you very much. And if you have any questions, please feel free to ask throughout the sessions. Thank you.